Okay, we're in section 12.8 of the notes, and we're going to talk through this first. This is the lecture portion. Again, the structure is the same every time for each section that we're doing. Right, a little tiny lecture, not long, not drawn out, not overly technical, at least I think not. And what we're going to be talking about over here is, I'll go to the whiteboard certainly, but we'll be talking about what an equal matrix is. And certainly we see a matrix over here. This is 3 rows by 3 columns. This is 3 rows by 3 columns. We'll talk about this one as well, a little more complicated, but we'll talk about it. It says they're equal. I got to find a condition that they're equal under, and I'll certainly go to the whiteboard later. We're going to start to introduce matrix arithmetic. Now, certainly at Essex County College, this is an introduction to matrix arithmetic. When you go further, like you start taking calculus, and then you start taking linear algebra, well, this is where things are going to start to be more formal. But right now, we're just introducing concepts about matrix arithmetic. And, certainly we'll talk about matrix addition. It's an arithmetic problem. We'll talk about what's called a scalar multiplication. Again, for those students wishing to look at little tiny videos instead of an entire lecture, if you're glazing over, you can certainly watch those tiny videos that they're helpful. We're going to talk about simple properties of matrices. Again, nothing to memorize. Hopefully you start to understand these properties. All right. I do want to point out in the notes, though, and this is really important, I'm going to be using notation that you should become familiar with. All right. And the notation is going to be this. The matrices, which have rows and columns in it, are going to be indicated with uppercase bold letters, whereas scalars, which represent single real numbers, are going to be represented with italic small case, or lowercase, I should say. So it's a lowercase c, lowercase d, indicating a scalar. A scalar is just going to be something to do with scaling, making things bigger or smaller, or possibly shrinking them to 0. All right. So again, just look in the bottom of these things. We hope you're reading these things over here. Not that you memorize what you read, but the more you read, the more it's going to start to sink in and make an impression upon you. All right. So in mathematics, real numbers are called scalar. They're used here simply to scale a matrix. We call it scalar multiplication. Again, we'll talk about the properties of it. All right. We'll go through that. Again, I want to point out, if you look at these things over here, some of my notes, I can clearly write down bold uppercase letters that represent matrices, and I can use these lowercase italicized letters to indicate scalars. All right. One's a number, not so bad there. And I'm still seeing that the scalar C and D. All right. Let me go to the whiteboard and give me a moment to switch over, and we'll talk through it. Again, talking through something doesn't mean you understand what's being presented. We'll go to examples, and hopefully it's going to be more understandable when we start going examples. But first lecture, let's talk about that first. All right. So one thing I want to point out is, looking at the matrices, I'm seeing my whiteboard over here. Let me just blow this up a little tiny bit. And what I'm going to do is just, briefly talk through this. And as I'm talking through it, I want to point out, it says 2 matrices are equal if they're the same dimensions. All right, so they could be equal if they have the same dimensions, but there's another condition: their corresponding entries must be equal. So let's look at an example. And the example I want to look at is the first example over here. And I want to point out the first matrix is 3 rows by 3 columns. Right, I see that right over here. The second matrix is also 3 rows by 3 columns. So the 3 by 3, all 3 by 3. So that condition's been met. All right. What's the other condition? That the entries are identical. All right. So what does that mean? This is the same as this. This is the same as this. This is the same as this. So forth and so on. That every entry in their corresponding place is the same. Every entry is the same. And if it's not, I would say they're not equal. So it's a clear example of 2 matrices that are equal. What am I saying? They're both 3 by 3, and their corresponding entries are the same. Let's look at the next one. This one over here. They claim they're equal. So let me write this down for you. The first matrix is a 3 by 3. The second matrix is also 3 by 3. Now I'm going to outline what entries I'm seeing over here. I'm seeing this and this. They have to be the same. Now we'll get to the condition later. This and this, they are the same. That's not a problem for me. This and this. Well, they're the same. That's fine. This and this, they're the same. Now, something over here, they say these are the same, and there's going to be a condition that makes them the same. I don't know what that is yet. This is the same. This is the same. This is the same. This is the same. Now, by the way, I don't know if they're equal. I'm going to start to outline things to you that I really need to wonder, are they really equal? For example, this, is it really equal to this? Well, I don't know. There's a condition that would make that true. All right, let me keep going. Is this equal to this? I got to say there's a condition that could make that true. All right, now what else do I say? This equal this. All right, let me write down one at a time for you, and I want to see if I can make them equal. So for example, the first one I'm seeing, that's row 1, column 1. In both of those matrices has to be the same. All right, now what would be there? I take x from both sides, I get x equals -1. So I'm going to say if those entries are equal, the condition under which they're equal would be this. All right, let me go to the next one I'm seeing. And what do I see? I see y minus 2, and that should equal 3 minus y. And I should be able to solve that as well. I would add y to both sides. That would give me 2y. And I would add 5 to both sides. I'm sorry, add 2 to both sides. I'm sorry, I think it's 5. Now, I'm going to say that looks pretty reasonable too. Y would have to equal 5 halves. Now, by the way, what do I know? I know row 1, column 1 is equal now. I know row 2, column 2 is equal. I don't know about row 3, column 3 if it's equal. So I'll write this down. What does it say? Row 3, column 3 is -6 on the left side. And what is on the right side? It's x. Well, I believe x is -1 minus 2y. What's y? 5 halves. I don't know if that's true, and I got to make sure it is true. Otherwise, I'm going to say they're not equal. So -6, -1, and this would give you what? Well, the 2's cancel, you get -5. That's certainly true. So what's a condition? These are the conditions that make it true. Of course, that's clearly written. All right. Let's go to matrix arithmetic. Let's carefully walk through it. And as I do that, I want to point out there is a footnote there that we're going to encourage you to read it. All right. So let me read that to you. And we're on matrix arithmetic now. All right. You'll be asked to add matrices, multiply matrices by scalars. That's what this section's about. By the way, there's other operations with matrices, but in this section, that's all we're going to ask you to do. And we're going to keep the arithmetic very, very simple. And notice there's a footnote over there. It's footnote 48. Let me go to that. I know I read this to you before. I want to make sure you're reading these guys over here and paying attention to this. What does it say? In mathematics, real numbers are called scalars. They're used here to simply scale a matrix through scalar multiplication. All right, let's take a look. And the next thing up, we talk about matrix arithmetic. What do we talk about? Scalar multiplications and adding matrices together. Well, let's talk about addition of matrices first. All right, right over here. It says if we have two matrices of the same dimensions, we can add them together by simply adding their corresponding entries. All right, let me go through this one step at a time. It's pretty simple. This is a 3 by 3, and this is a 3 by 3. What do they say? We can add those matrices together by adding their corresponding entries. And we're going to end up with a 3 by 3 if we do that. All right, let's take a look at one step at a time. I'm adding, oops, sorry about that. I'm adding this to this. And what would that give me? Well, if you add those together, you'd get 1. Fairly simple. You're going to add this. These are corresponding entries, by the way. Row 1, column 2, you would get 0. You're adding this to this. That's row 1, column 3, you get 7. This to this, you add them together, you get 5. This to this, you would get -1. Again, I'm adding corresponding entries. -5 and 7, 2, fairly simple. -3 and 1, -2, 2 and -1. Now, sometimes do you make mistakes doing this? Yeah, you do. That's where machines come into play. The problem with using machines over here, it's harder to type these things in than it is to do the arithmetic. That's so true. Sorry about that. So I'm going to say fairly simple to do, fairly simple. Scalar multiplication, let's talk about it, all right? And then we'll look at properties next. but scalar multiplication. We're looking at this over here. A scalar is a real number, all right? Now, what kind of real numbers you got? You got integers, you got rationals, which are ratio of integers, and you got irrationals, which can't be written as a ratio of integers. What are we going to do? We're going to multiply a matrix by a scalar. Now, someone says, why they call it a scalar? It actually scales the matrix. You know, it either going to expand it or contract it or possibly shrink it to nothing, right? So I'm going to say what we do is we multiply every entry of the matrix by the scalar multiple. So for example, over here, the scalar is 5, and we're going to multiply every entry by 5. What would you get? Minus 5, minus 15, 10, 25, 20, minus 25. I'm just verifying what I'm seeing. Minus 15. This would give me 10. Last but not least, I get minus 5. Fairly simple operation, right? Let's go to the next thing, which can be simple properties. Now, really not much to say about it. Kind of simple properties. Just like when you're in grade school, they gave you simple properties. You know, they might have said, you know, additions are commutative, multiplications are commutative, something about the distributive property multiplication, associative property of additional multiplication. A lot of properties, right? So let's talk about this. I think I know I mentioned this in lecture, but I'll go through it again. When I use these notations over here, A, B, and C, you should notice when I'm typing this up, that A, B, and C are bold letters or uppercase. These represent matrices. So I'm going to say right now, A, B, and C are some matrices, all right? They all have the same dimensions, by the way. What does that mean? They all have the same number of rows, same number of columns. Then they go on to say that C and D are scalars. What does that mean? They're a real number. All right. Now you should notice the difference immediately. A, B, and C, the uppercase letters are in bold, and those lowercase letters C and D are written in italic. They're lowercase, right? Real number, right? So we have the following. Let's go to the next page. And certainly I'm going to say it looks pretty simple to me. I'm going to say maybe you start to relate this back to what you learned in grade school. Let's talk it one step at a time. All right. Associative property of scalar multiplication. And that's written over here. Now, what are they saying? They're saying if you did this thing, well, you could associate the scalar C and D before multiplying the A, or you may decide to associate the D, that's a scalar, with A first, and then do C later. It's entirely up to you. By the way, you know something, property of multiplication, you can commute the C and D around if you like as well. All right, let's talk about the commutative property of matrix addition. What does it say? The matrix A plus the matrix B is identical to matrix B plus A. That's pretty simple. Scalar identity. 1, that's a scalar multiple of the matrix A, returns A. That's pretty simple. Something you could think of. Distributive property. What are we saying? The scalar C distributes because the sum of these two metrics. Here's the deal, though. You may decide to add these two together first, or you may decide to do the scalar multiplication and then do the addition later. It's up to you. Associative property of matrix multiplication. Again, pretty simple. What are we doing over there? Well, you could decide to associate B and C first, or later on, maybe you want to do something different, associate the AB first, and then do the C. All right, we'll go through examples. The examples will follow. Thanks for paying attention.